So we want to start. We had a sort of a free range discussion last lecture about what is probability, what is random variables, histogram, counting, binning. Now we want to get more quantitative. I want to start with a few definitions, and today I want to discuss what are called discrete random variables or discrete probability distributions. So we talked about what are random variables. Any quantity that can take a range or a distribution of values is called a random variable. There are two classifications primarily, discrete random variables and continuous random variables. Discrete random variables are usually those that you can count, like a coin flip has two outcomes, a roll of a dice has six outcomes. It could be number of rare events like number of earthquakes in a period. It could be situations related with playing cards, or in other words, a finite set of outcomes. Okay, those are all usually discrete random variables. For such discrete random variables, usually takes the probability is defined as probability that a discrete random variable, we'll call it uppercase X, takes a specific value A. So we'll say probability of X equal to A. It could be defined as the number of outcomes that are favorable to that value of A divided by the total number of outcomes. For example, you know this, what is the probability of getting ahead? There are one favorable outcome, but there is one favorable outcome and two outcomes in total. So 1 divided by 2. Or what is the probability of getting a dice showing a 4, which is 1 over 6? Example, right? So we, for discrete probability distributions, which is what we are entirely going to be focusing on today, we'll get to this next lecture hopefully. The discussion starts in knowing what is the probability. So if I ask you the question, what is the probability that a outcome of a dice, or let's say that is denoted as x is greater than or equal to 3. When you roll a dice, you may get anything from 1 to 6. What are all the times in which the outcome is 3 or more? How many cases favor that? 3, 4, 5, and 6. 4 outcomes in favor of what your situation is divided by 6 outcomes total. That makes it 2/3. There is a 2/3 chance that any time you roll a dice, you will get a 3 or more. That's the idea, right? So I can ask the question, what is the probability of getting a 1 or a probability of getting a 2 or getting a 3 and so on up to getting a 6? What is the probability of getting anything between anything 1, 2, 3, 4, 5 or 6 when I roll a dice? 1 out of 6. Or like 1 is a victory, 2 is success, 3 is success, 4 is success, 5 is success, 6 is success. That's 6 on 6, right? So this is 6 favorable outcomes divided by 6 total number of outcomes, which is equal to 1, or in other words, getting any number when you roll a dice is a certainty, which makes this a certainty. Of course, the word probability itself means something is not certain. A certainty is kind of like the limiting case of a distribution where if you roll a dice, you're going to get something. That's what this statement means. Okay. So in general, we can write the sum of the probability of x taking a certain value, I equals 1 to, let's say, total is equal to 1. This is just saying the sum of all the sum of the probabilities of all possible outcomes is 1 or 100%. I'll let you write up to here. Okay, because I kind of started here. Maybe you didn't have chance to write that down. Did you all bring coffee? It's going to be rough, so bring coffee. I want to cover a lot of concepts so that in the last lecture on this topic, we can do that simulation and make a prediction of the election outcome this fall. Okay, we are still on plan to do that. Okay, so this we start with the notion of what is the probability, which is x taking a specific value. Okay, x is our random variable, which could be any of these. So let me give you a card example. So if I have x denoting a certain card, like for example, if I draw a card from the deck, what is the probability that x is less than or equal to 10? Remember, playing cards have 1, 2, 3 up to 10, and then they have J, Q, K, and A. So that's the 10 plus 4, right?
There's no 1.
Oh, there's no 1, sorry. Not a big gamble. So 13 cards, okay, and I know there are 4 colors. 4 colors. So that makes it 13 times 4 equals 52 cards. So 52 is your sample space. This total here is often referred to as sample space, and this is the number of favorable outcomes. It took me about 10 years to lose the U. I used to write favor with the U, like British people do. It took me 10 years to get rid of that habit. Okay. What are the number of favorable outcomes where the card, if you draw randomly from a deck, you are going to get a 10 or less? 9 times 4, right? 9 times 4 by 32. Oh, you didn't say 32. So if you simplify this, this is 9 over 13, which you can write as a fraction. I mean, it's about, you can do the fraction, okay? But the idea is you can define a certain event and then evaluate what is the chance of that event. Okay, that is called probability. With me so far? Good. Okay. So which part can I erase? Can I erase this? Yeah. So we saw what is probability. Okay. Next thing we want to do is what is cumulative probability? Like for example, let's say there are let's assume, let's say x takes a sequence of values such as x1, x2, x3, and so on up to xn. This could be, for example, x1 equals 1, and then x2 equals 2, x3 equals 3, and so on, x6 equal to 6. This is like a dice. Or another example is the playing cards where you have x1 equals 2, x2 equals 3, and so on, x9 equals 10, and x10 equals j, and so on, x13 equals 8. This is like the playing cards. Okay, let's say x takes a sequence of values Again, when you do discrete variables, these values are just labels. They could be the side of a dice or a coin, head or tail. It's just a label for what your outcome is. Okay. So if I say probability that x takes a certain probability of x equals xi, which for short I'll write probability of xi summation I equals 1 to 1 to 1 to n lowercase, where this n is less than or equal to uppercase n. Consider this summation, okay? The probability that we add up the sum of the probabilities for x taking the first value up to lowercase n, where lowercase n may be the uppercase n or the limit or something lesser than the limit. Consider this. What is summation I equals 1 to 4 probability of xi for the case of the dice? Can you compute that? This is probability of x1 plus probability of x2 plus probability of x3 plus probability of x4. What is x1 represent? Getting a 1. Getting a 1. Getting a 1. This is getting a 2. This is getting a 3. This is a 4. What is the chance of getting a 1? 1/6. So this is 1/6 plus 1/6 plus 1/6 plus 1/6, or this is 4/6 or 2/3. Okay. In general, I want to keep this. Okay. So I'll wait for a second. Let me know when you're ready to move on. In general, the summation of I equals 1 to m probability of xi is the cumulative probability that x assumes values lesser than or equal to xn. Summation from 1 to xn is essentially telling what is the chance that this random variable takes progressively higher values. Okay. Maybe that's little mathematically obtuse, so maybe I'll try to say that more intuitively. What is the probability of getting a head in a fair coin? So if I write head and then tail, what is the chance? 50% and 50%. Okay. Now this is probability. When I try to plot the cumulative probability, okay, when I get head, that is when I am interested only in the first outcome, this is 50%. If I add up the first outcome and the second outcome, and when I get to the second outcome, what is the chance or what is the value of the cumulative probability? It includes everything up to that point, which is the 50% for head and another 50% for the tail, which will make this 100%. 100%. That makes sense. Cumulative probability is adding up all the outcomes until that point. Does it or does it not? I'll give you one more example. What is the chance of getting a 1 in a roll of a dice? 1/6, right? So if I plot this, if I write 1/6 here, the chance of everything is the same. It's 1/6, right? Okay. This is probability. Probability. When I say cumulative probability, remember cumulative probability, we'll give it a symbol. F of xi is equal to summation, sorry, f of xn is summation I equals 1 to n probability of xi. So this is f of xn. Okay. This is n. When n equals 1, we are thinking about dice. What is f of x1? That will be I equals 1 to 1 probability of xi, which is like writing probability of x1, which is 1/6. You're with me at this point? So the first point I will plot here is 1/6. What is f of x2? F of x2 f of x2 is summation I equals 1 to 2 probability of xi, which is probability of x1 plus probability of x2. What is the chance of getting a 1 and then add it to a chance of getting a 2? 1/3. 1/3, because this is 1/6 plus 1/6. So if I were to plot f of x2, which is the cumulative probability function, that will be 1/3 for n equals 2. So you are going to get like a step function and so on. Okay, you're going to get a step function that ultimately for n equals 6, it will reach a value. Can you guess? For n equals 6, what is, so if you do this f of x3, f of x4 and f of x6, can you guess the value of f of x6? 1, right? 100%. Why?
You add all the previous ones to it.
If you start at the first point and you add up all the outcomes, the sum of all the outcomes is a certainty. It's like asking at the end of the election, will we have a president? Of course, we'll have a president. The president elects, right? Because it is a certainty. Who will be the candidate is a probability. So this cumulative probability gives you a way to understand how the distribution evolves in terms of the possible outcomes. Okay. Did that kind of gel with you? So you know very well that if you had a coin with you, you flip it 50 times, you are likely to get an almost even number of head and tails. Okay. All right. Let's start there. I want you to generate. Okay, here's a question in front of you. Generate a sequence of 10 coin flip outcomes. Not that you can just make up something and write 5 head value, 5 tail values arbitrarily. What we want to do is generate a sequence of 10 outcomes using this principle, which is here is head. What is the cumulative probability distribution function when you have a head? The probability of getting a head is 50%, 1/2. Probability of getting a tail is also 1/2. Instead of calling them 1/2, we'll call them P and 1 minus P. You're with me so far? P and 1 minus P. What is the probability? That is, if I say f of x1, this is summation I equals 1 to 1 probability of x1. X1 is nothing but a symbol for h, which is like saying P. What is f of x2? F of x2 is I equals 1 to 2 probability of xi, which is probability of a head plus probability of a tail 1 minus p, which adds up to just 1. Okay, so if I were to plot it, I would get 50% here, and by tail I would get 100% here. Okay, here is where we are going to do some magic. Not necessarily magic if you understand it, but something new. I've now given you a task. Generate a sequence of 10 coin flip outcomes according to this probability distribution. This P could be 53% or 0.53, and this 1 minus P is 0.47. Okay, or this P is Mr. Trump's polling, which could be 51%, or Miss Harris polling, which is 48%, something. If you look at this y-axis here, what do you notice? What is the range of variation of the value of this cumulative probability function? Over here with the dice example, it starts at 1/6, goes up to 1. Or if you take one outcome to 6 outcomes, it varies between 1/6 to 1.0. It starts at 0 and goes up to 1. It starts at 0 and goes up to 1. Okay? If I randomly select a number between 0 and 1, it can be any number. Let's say I select 0.495. 0.495 would fall somewhere here. Or if I select 0.91. Or if I select 0.23. Okay? Depending on where it meets these probabilities, I can call it a head or a tail. The most relatable example is in an election, 50.001% is enough for a candidate to win as long as he or she has one vote more than the other. Right? That's what an election is, right? It comes down to basically one vote. One vote is higher, that candidate wins. So the way we generate a sequence of 10 coin flips is that we generate 10 uniformly distributed random numbers, something that has an equal chance of being anything between 0 to 1. And depending on that chance, if it is below our slider, it is a head. If it is above our slider, it is a tail. And where you place the slider is arbitrary. I said it's P, right? P can be 0.6. It could be a biased coin with one side being heavier. Let's say we keep the slider at 0.6. So if you generate a uniform random number between 0 to 1 and it comes above 0.6, it's a tail. If it comes below 0.6, it's a head. So if you do it this way, if you generate 10 random numbers, 10 uniform random numbers, they are uniform by definition. That is, they will fall somewhere between 0 to 1 with equal odds. A uniform random number has equal or uniform probability in a range A to B. That's why it's called uniform. Okay. So if you had a magic 8 ball that can generate uniform random numbers, by extension, you can generate binomial random numbers. Can you? By binomial random numbers, I mean simulating a coin flip or simulating the outcome in an experiment with only 2 outcomes. Are you with me so far? Is this thread making sense to you? If I give you that uniform random number, can you run it 10 times and generate a sequence of 10 coin flips for me? Do you have your MATLAB with you? I'm going to do it on the screen, okay? So you can see this. All right. You don't have to do it immediately with me, just watch and somebody has to keep talking back to you. All right. You don't have to do, just watch for a while, okay? All right. So first thing I want to show you is if you go to MATLAB documentation and type uniformly distributed random numbers. So type this, basically this phrase in the help and you will end up with this page. This command here says rand, that is a subroutine in MATLAB which generates uniform random numbers between 0 to 1. So if you run it 100 times, you will get 100 numbers. And if you do the histogram of that 100 numbers, it will look like a flat line. That is the idea. So I'm going to take that rand, okay? So I need a volunteer who will note down the outcomes. Our probability right now is 50%. We'll start there. Okay, we are targeting a fair coin with a probability of head of 50% and tail also 50%. So I'm going to type rand and it spits out 0.8147, which makes this a, if it's above 50%, it's tail, below 50%, it's a head. This is a tail. So I want one of you to write that down. We are going to do it 10 times. So this is like, I got one tail, okay? Again, let me run this function. 0.9058, another tail. So T and T, okay? And then I'm going to run this again. 0.1270, TTH. I'll start noting it here. TTH. Probability of 50%. So we got, first time we got something like 0.81, 0.82, I'll write 0.9, 0.91, and then 0.13. All right, we'll go again. 0.91 again. So this is another tail. 0.63, another tail. 0.0975, which is a head. 0.10. 0.2785, another head. 0.28. So that's 7 trials so far. and then 0.5469, which is a tail because it's over 50%. 0.9575, another tail. 0.96. So we have 4, 8, 9, one more. 0.96 or 0.97, another tail. So we have 3 plus 2, 5 plus 2, 7, 7 tails and 3 heads out of 10. If I just told you this, what would your inference be? You think the coin is biased, wouldn't you? Right? How do you actually understand if the coin is biased, or if we have we done enough trials? So like if you did, let's say, only 2 trials, you just only did the first 2 trials, you got 2 tails. Would you conclude that this coin will always give you tails? Of course not. You will do more trials, right? So the key to getting statistical convergence or confidence is to increase the number of trials. So if you repeat this experiment, let's say 100 times or 10,000 times or 100,000 times, by doing a lot more number of these trials, you will be able to exactly recover the value of the probability. Suppose we had set the slider not at 50%, but at 60%. What would the outcome look like then? These 3 will still be tails. This is a head. This is a tail. This is still a tail. Tail, a head, head. But this is no longer a tail. This will flip as a head. Right? So you will have 6 tails and 4 heads. Which still looks odd because the probability of getting a head is 60%, but your trials suggest the other way. Okay, so what I meant to show in this example is, how do you generate a sequence of random numbers if you know what that probability distribution or what that probability is? Okay, so can somebody describe to me how do you simulate the roll of a dice? Like if you roll the dice, let's say 20 times, you're going to get a number each time. How do you simulate that sequence without actually rolling a dice? For a fair dice, where is your slider?
Do multiple sliders, right? 6, 1/3,
1/6, 1/3,
1/2,
1/2,
5/6,
2/3,
5/6.
5/6, and then 1. If you generate a random number, it's going to be between 0 to 1, right? You just need to place it on the scale. So the scale, the cumulative distribution always in uppercase and underline varies between 0 and 1. So I generate a random number. Okay, it has to fall between 0 to 1. That's the idea. If it falls in this window, I'll call it a 1. If it falls in this window, I'll call it a 2. If it falls between 1/3 and 1/2, I'll call it a 3. If it's between 1/2 and 2/3, 4. Between this, 5. And between these two, 6. So this is your cumulative probability, and these are your outcomes. So those who have MATLAB, you don't have to write any program. Just go to the command window, type rand one after the other 10 times, and get me 10 outcomes, like a sequence. So I want you to fill out this table. Uniform random number, which will use the symbol R to denote, and then we'll say outcome. So I want you to manually do this. I'm not asking you to write any programs. Run that rand syntax once, look at the number, place it between this, and write down the outcome. Go ahead. Tell me one, give me an outcome. No, this is not an outcome. This is just me writing down the scale and the possible outcomes. So run your rand once. 0.8147. What is the outcome for that based on this scale? How much is 5/6? 5/6 is 0.83. You are just below 0.83, which will put you in for 5. You go now.
That's the same number.
I think MATLAB just starts with the same sequence. Okay, so maybe we want to do. Okay, let's do this. We'll say rand of 10. So that, okay, it gives me a matrix of 10 by 10. Okay, it gives me a matrix of 10 by 10. I'm just going to take the first column, and based on that, I want each of you to look at the number and tell me the outcome. So if you went first, based on 0.15, what would you say? How much is 1/6? Sorry? 0.167. So 0.15 would place you in 1. So we'll say 0.1576 will place you for an outcome of 1. Do you want to go? What is your name? 4. Do you want to pick one number and tell me, pick the second number and tell me the outcome?
The 6.
6, because it's almost close to 1. So 0.97 would be 6. Lauren. 0.655. Good. What would that be? This is 50%. 2/3 is 0.67. 0.655 would be 4. 0.655 would be a 4. Do you want to go? Yeah. Pick one number. 4854. 4854 is just short of 50%, right? So this is 0.33. And so this should be 0.4854 should be 3. Mary. This one. Okay. Point 1419. How much is 1/6? So 14, 16. What would the outcome be? One. So you get the hang of it, right? You generate a random number, but before that you need a lookup table. Okay. So this we covered 2 distributions here. One is binomial, which has only 2 outcomes. That's why the word bi appears. And then this is a uniform distribution. That is a uniform dice has sliders that appear at 1/6 intervals. So it goes from 0 to 1 in spacings of 1/6. Okay. With me so far? All right. So now let me stop the sharing for a second. To the do the sliders, that is what I call these as sliders, do the probability values, do they have to be uniformly spaced? What if you had a dice which is rigged to get you a 1 or a 3 more often than the others? Suppose this rigged dice doesn't have a 1/6 probability, maybe it has a 1/5 probability of getting a 1. Okay, so first 20% is for 1, and from 1/5 to 1/3 it is a 2, which means the chance of getting a 2 has been reduced. And between 1/3 and 1/2 we get the 3, but let's say we write this not as 1/3, let's say this is 1/4. So this is 20%, this is 25%, and then this is 50%. So it's like there is a 25% chance for getting a 3 and a 20% chance for getting a 1, but only a 5% chance for getting a 2. This dice is so rigged, okay? And rest of it is same. If you now generate a sequence of uniform numbers, you will get more 1s and 3s and very fewer 2s. Do you see that? So the probabilities that appear here, that is, if I write this in a fresh space here, okay, the probabilities, I'll write them as P of xi, okay, where you will have, let's say, I equals 1, I equals 2, I equals 3, and so on, I equals n. Those probabilities can be non-uniform, meaning you could have a higher outcome for one and a lower outcome for the other, and so on. If that is the case, your cumulative probability, which is f of xn, f of xi, xi or x? Yeah, f of xi, which is summation from that point, from the beginning to that point, p of xj. And this is I equals 1, 2, up to n. So this will be non-uniform. So this slider could be all the way up to, let's say in our example, this could be 20% or 0.20, and then you have 5%, which is 0.25, and then you have 3, which is at 50%, 0.50. So you have this at a short climb and then a large climb. Okay, so you have seen uniform probability, you have seen binomial probability, which can be even or uneven. And you saw the playing cards, the rolling dice and everything, which are all sort of, you can make it either uniform or you can make it slightly non-uniform. We are going to see as the next distribution in our list, a very, very, very important and useful distribution called the Poisson distribution. The Poisson distribution. Now, what is this Poisson distribution? Just like, I'm going to write it out, just like the probability of xi taking a head or a tail is equal to p, or the probability of xi taking a 1 or a 2 or a 6 is equal to 1/6 in a dice. The probability of x taking a specific value xi is given as e power minus lambda, lambda power xi divided by lambda factorial. Yeah, correct. Where xi can assume values starting from 0 1, 2, and so on, only non-negative integers. Only non-negative integers. So if you later watch this in video, I forgot to move the camera, but now I have. So the audio will appear first and then the video will catch up. All right. So Poisson distribution, probability of x assuming a specific value is given as e power minus lambda, lambda power x divided by lambda factorial. Sorry, divided by x factorial. And remember, x is a non-negative integer. It can't be a real number, it can't be a negative number. What are the kind of quantities we use to model? We use the Poisson distribution to model. X can be usually number of events. Like for example, we discussed about earthquakes, let's say. Rare events. Lambda is called the mean parameter. Mean or average parameter. Okay. So if x assumes values, let's say 0, 1, 2, and so on, let's calculate lambda. If I say something is the mean parameter, that is like writing this is summation of x taking a certain value multiplied by the probability of x taking that value. Where am I getting this from? We saw this or we talked about this when we were doing histograms. Remember in the histogram, we said the average is the frequency with which something appears multiplied by the midpoint summed over all the bins. That is exactly this idea. This probability is nothing but your frequency. That is, if you divide the frequency by the total, that is your probability. Can you write out this summation and see what happens? So I'm going to write lambda equals summation I equals, I should write I equals 0 to I equals 1. I'll write this as x times p of x, where x runs from 0, 1, 2, and so on. Okay, so this is like 0 times p of 0 plus 1 times p of 1 plus 2 times p of 2, and so on. It goes on up to infinity. You've seen infinite series before, right? Somewhere in your calculus or differential equations. So what is p of x? I gave you a formula already. that is e power minus lambda, lambda power x divided by x factorial. So let's put this into these expressions. So I'll have, what is p of 0 then? E power minus lambda, lambda power 0 divided by 0 factorial. I'll give you time, take a break. What is this? Tell me. E power minus lambda times, what is this? 1 divided by 1. So this is just e power minus lambda. Okay. What is p of 1? E power minus lambda, lambda power 1 divided by 1 factorial. I promise I'll give you time to write. Okay, so this is e power minus lambda times lambda. Okay, what is p of 2? E power minus lambda, lambda squared divided by 2 factorial. So you can do this all day. I want you to just write it up until, substitute these into the expression and then I'll continue. I'll give you time to write. So lambda, which is summation x p of x, is 0 times e power minus lambda plus 1 times lambda e power minus lambda plus 2 times e power, 2 times lambda squared e power minus lambda divided by 2 factorial plus 3 lambda cube e power minus lambda divided by 3 factorial and so on, goes on. Okay, so what do we get? We can factor out e power minus lambda from everything. You get lambda plus 2 lambda squared divided by 2 factorial plus 3 lambda cube divided by 3 factorial plus and so on up to infinity. I can extract one more lambda from here. So this is lambda e power minus lambda. Wait, am I doing it first?
The first one, the lambda would be a 1.
This one?
No, go in the parentheses, wouldn't that just be a 1 right there?
Yeah.
No, it's, you said you have lambda plus in the parentheses, right there, that should be a 1.
No, this is 0. This is 0 times x. It's starting.
So you take that out of the out.
No, this just goes away, right? I mean, you don't have to write a 0. It's just 0. Wait, before that, I'm actually wondering if I'm doing something wrong here. Let's see here. I want to step back, take one step back. Okay, first thing I want you to do is not calculate lambda. Instead, I want you to compute for this probability function. What is the summation of x? Sorry, what is the summation of p of x where x assumes values starting from 0, 1, 2, and so on. Compute that first. That is, what is p of 0 plus p of 1 plus p of 2 plus and so on up to infinity. Can you compute that first? I think I missed a step in my thinking. Okay, so let's not do this first. So what is p of 0? Summation p of x equals p of 0. What is p of 0? E power minus lambda, lambda power 0 divided by 0 factorial plus what is p of 1? E power minus lambda, lambda power 1 divided by 1 factorial plus e power minus lambda, lambda squared divided by 2 factorial, lambda cube divided by 3 factorial, plus and so on up to infinity. This, if you simplify, this is e power minus lambda times lambda power 0 divided by 0 factorial is 1 plus lambda divided by 1 factorial plus lambda squared by 2 factorial, lambda cube by 3 factorial, plus and so on up to infinity. Does this look familiar to you? This is a series expansion for a very famous function. Can you identify it? No, close but no. Yeah.
Is it a little
The plus one.
plus series?
No, there is no such. I don't know anything.
There's like some series in calculus that uses the lambdas on the back of them.
Something. All right. So this is e power lambda. If you take the function e power x and write that as a power series, that would be 1 plus x squared over 2 factorial plus x cube over 3 factorial and so on up to infinity. This is exactly that, which is e power lambda, and then you have e power minus lambda. So this is e power minus lambda times e power lambda, which makes this 1. What is the basic tenet of probability? The sum of all the outcomes must add up to 1. Right? That we are able to recover. All right. Now, this lambda, I told you, is the mean parameter. Okay. It represents the average number of times an event is expected to happen. Expected to happen usually in a window or during a window of observation. During a window of observation. This is the example I mentioned last lecture. Based on seismological records, it is known that the California region, like Southern California region, is expected to have one major earthquake every 30 years. That is based on counting all the major quakes, let's say in a 200-year period, divided by 2. It doesn't pay attention to when those events happened. All the events they counted could have happened in the first 40 years and then nothing for another 160 years. It could be the case, but all that is not considered. It just takes the average number of times divided by total time. Okay, so if we start with that example, let's say lambda is the number of major quakes, number of major quakes per year. I told you based on USGS data, the rate is one major quake every 30 years. 1 in 30 years. If you were to turn that into a rate of some event per year, what would that be? I'm telling one event every 30 years. If I ask you the other way, how many events per year, what would you say?
1/30.
1 over 30. So this is nothing but 1 over 30. One event per 30 years. Or making it 1 by 30, 1 divided by 30 events per year. This is your average parameter. Now I'm asking you to calculate if one lives there for 30 years, what is the probability of experiencing exactly one major earthquake? Can you answer that question for me? If lambda equals 1 over 30 per year, what is the probability that you will experience exactly one earthquake if you live there for 30 years? Sorry, I shouldn't say lambda is 1 over 30. That is, the data says you will get a major quake every 30 years, which means it is about one event, 1 by 30 per year. Now the question is this: how will you answer this question? Think about it. Let's stop. So lambda is always some average number of events. In my case, the odds are 1 by 30 events per year, and we are spending 30 years in that region, right? So that is, I have to multiply this by 30 years, which will make it one, on an average, one event during the window. One event. I think you are very distracted. You are distracting me. One event during the window of observation. Do you see the difference? That is, your rate doesn't change. It's based on data. It's always one event every 30 years. You might spend 30 years there, or 15 years, or 60 years. For that period, the average is 1 over 30 multiplied by 30, which makes it one event during the time that you are interested. If your window of interest is only 5 years, instead of 30, you would just multiply it by 5 years, which will make it 1 over 6. Or if your window of interest is 200 years, you will multiply by 200, and then that will be 200 divided by 30. Okay, so the window of interest can change, but the rate is based on data. So this rate is based on data. This is based on our preference. So with this lambda value, that is lambda value of 1, I want you to calculate what is the probability of experiencing exactly one earthquake. That is, if X denotes the number of events, I'm asking you what is probability of X equals 1. How will you get that? E power minus lambda, lambda power x, which happens to be 1, divided by x factorial. So e power minus 1 multiplied by lambda, which is, we'll come to lambda, sorry, e power minus lambda multiplied by 1 power 1 divided by 1 factorial. Or this is e 1 over e. How much is 1 over e? You can use your calculator to tell me what is 1 over e. Is it 0.37? 368?
0.36.
Okay, 0.368. So the probability of experiencing exactly one earthquake is 0.368. If you want to put it in words, there is a nearly 37% chance that you will at least see one earthquake if you lived in a zone where the rate is roughly one event every 30 years. Okay. Now go ahead and tell me what is the probability that you will see two earthquakes if you lived in the same zone for the same 30 years. These are all exam questions right here. Don't take them seriously, okay? So probability, so probability of experiencing one quake is 0.368 or nearly 37%. What is the probability of experiencing two quakes? That would be probability of x equals to exactly two quakes, not like one or two, it's exactly two. That would be e power minus lambda, lambda power x divided by x factorial, e power minus 1, 1 squared divided by 2 factorial. So this is 0.368 divided by 2 or 0.184. 0.184 or nearly 18%. So there is a 37% chance you will experience one quake. There is a 18% chance you will experience two quakes. What is your question? Yeah. 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 That's just a coincidence that this formula works out like that. Yeah. Usually it may not. Okay. Because we have lambda equals 1 in this particular problem, it just is convenient. Now answer this question for me. What is the chance that you will experience at least one quake? Is it the same as this? That is, if I rewrite the question, and say the probability of experiencing at least, it's a very important word, at least one quake. What is that? That is, it's like saying probability of X taking at least one which means it can take 2, 3, 4, 5, and so on. When you say it's experiencing exactly one quake, X can take only the value 1. It cannot take 0 or 2 or anything else. When you say it is experiencing at least one quake, it could be 1, 2, 3, 4, and so on. So this is like writing probability of X equals 1 plus probability of X equals 2 plus probability of X equals 3 plus and so on up to infinity. Are you going to sit there all day and do this infinite number of terms? What shall we do? As if coding is easy. What will you do? You don't have to do coding. You can do something simpler. This is from 1 to infinity without the 0, without the first term. You do know something about when you add everything up from 0 to infinity. What do you know? They all add up to 0. They all add up to 1, right? Sum of all the outcomes should add up to 1. This is all the outcomes except one outcome, which is the X equals 0. Right? So this is like writing. I can take this and add probability of X equals 0 and also subtract probability of X equal to 0. Add and subtract. So I can group this guy with the rest of the gang and call this 1 minus probability of X equal to 0. It's like saying that the probability of experiencing at least one quake is 1 minus the probability of experiencing no quakes. Yeah. Lambda equal to 1 came from so lambda is the average number of events in the window of observation. In the window of observation. Our window of observation happens to be 30 years, which we told in the problem. If I live there for 30 years, what is my chance? Okay, this is the window of observation. This rate of events, which comes from usually some kind of data, happens to be one event every 30 years. It's okay, maybe an unfortunate choice that I chose 30 years here and 30 years here that maybe threw you off. But if I had chosen, let's say I lived there for 5 years. That's exactly what I just made like 2 minutes ago. In this case, if it is 30, lambda is 1 over 30 multiplied by 30, which is equal to 1. Okay. Okay. So can you get me this value 1 minus p of x equals 0? What is p of x equals 0? 1 minus e power minus lambda, lambda power 0 divided by 0 factorial, which is 1 minus 0.368, or this is 0.63, or about 63%. That is, if you are in a zone in which there is a major earthquake every 30 years, there is a 63% chance that you will experience at least one. That is the inference or interpretation. Did you hear that? Did you get that into your system? There is a 63% chance. Okay. We can concoct all kinds of questions. Like for example, what is the probability of experiencing 3 quakes? More than 2 quakes? No more than 4. Just tell me this. How will you define if I ask you probability of no more than 3 quakes? That is probability of what? X assuming what type of values? You know the answer, tell me. X less than or equal to 3. So that X never exceeds 3, that is the point, right? Or if I say X or the probability of no less than 2, which means X is greater than or equal to 2. So it's basically wordplay. Exactly, at least, at most. 3 words. Exactly, at least, and at most. Okay, or I can say what is the probability that I will have 1, 2, or 3 major earthquakes? X assuming values between 1 and 3. This is nothing but probability of X equals 1 plus probability of X equals 2 plus probability of X equals 3. Okay. With me so far? Okay. At least for this topic, I strongly suggest that you try to watch the lecture again and do some examples that are given in the homework. Not at least for this topic, for all the topics, but if you don't do examples, statistics will never stick. It'll always be like it'll make sense. Maybe even now it doesn't make sense, but even if it makes sense now, later it won't. Okay, so it's a tough subject. Okay. All right, so I want now to think about plotting the probability P of X versus X. For X equal to 0, what is our probability of 0 events? What is P of 0? E power minus lambda, lambda power 0 divided by 0 factorial, or 0.368. So the first bar will have a height of 0.368. What about X equals 1? Did we do that? Also 0.368. What is the probability of experiencing 2 events? 18%, or 0.184, half of it. Without doing the actual calculation, can you tell me the trend? That is, when I think about X equals 3, do I expect that to be let's say half of the previous, or even lesser than half of the previous? What is P of X equals 3?
0.0613.
E power minus lambda, lambda cube divided by 3 factorial. Right? What was the number?
0.0613.
0613. So 0.0613. What is half of 18%? 9%. So if it were 9%, you might even think it's falling linearly, but it's falling even faster than linear. It's falling exponentially, or no? So when you think of X equals 4, this is e power minus lambda, lambda to the 4th, 4 factorial. Can you also help me with that? For x equals 4,
0, 1, 5.
0, 1, 5,
3.
3. So this is already down to 1% chance. Look up, listen. 37, 37, 18, 6%, 1.5% chance. It's precipitously falling. Soon it will be negligible. So if you are in this zone, you live an average human lifespan, let's say you live a good life in 90 years, your chance of still seeing a lot of earthquakes is pretty small because by definition, these are all rare events. And the chance of encountering decreases pretty quickly. So clearly one thing is, number one, it falls pretty quickly. Number two, if you think about the cumulative probability, up to the first 37%, the outcome is a 0. Up to 64%, or 37 plus 37 is 74. Up to 74%, so up to 37%, you are getting 0. Up to 74%, you are going to get 1. Between 37 and 74. 82, 92%, nearly 92% to 2. And then 92 plus 6, 98% to 3. And then you are at 99.5 here near. And after that, it's not going to immediately go to 100. It's just going to go incrementally slowly. So if you are doing the random number sampling, you generate a sequence of 100 random numbers, your chance of finding a 6 is like pretty small. Your chance of finding a 12 is even smaller. But a chance of getting a 0 or 1 or 2 is pretty high. Okay, so I can rewrite that problem and say, generate a sequence of 20 Poisson distributed random numbers with mean parameter lambda equals 1 over 30. Sorry, mean parameter lambda equals 1. With this 1 happens to be 1 over 30 multiplied by 30 years. So what did we learn today? We learned about 3 distributions: uniform, binomial, Poisson. We learned about computing probabilities. We learned about computing the cumulative probability and also generating sequence of random numbers which mimic a binomial distribution or a Poisson distribution. The reason I am including this random number generation is because it's what will later be useful for doing that Monte Carlo simulation. And it's a pretty useful skill to have as engineers. Let's say you have a very simple machine which is made up of 2 components, just 2 components. Each component has an individual rate of failure. They are operating together. You can try to simulate this device or machine. How often will it fail? Like a collective probability for the failure if you know the individual rates of failure. For that, you need to run what is called as a Monte Carlo simulation, which is what I'm trying to go through here. So this will pick up and do more problems before going into the famous bell curve or the normal distribution next lecture. Okay. So 2 things, please try to rewatch the lecture. I know it might have been pretty intense. Second thing is do examples that I've suggested in the homework. Okay. Thank you.